Hey, how's it going?
Good, good. How you doing?
Cool. Not too bad, thanks. Greetings from South Africa.
Yeah,
Um, anyway, yes, certainly. But thanks for that presentation. That was great. So much information. I mean, as you say, this is niche of niche, right?
yeah,
this,
yeah,
yeah. Thanks for putting it all together. So I have a question I want to bounce off you. Last year, I did some work with the VST, and I've done quite a bit of FPGA before on LabVIEW.
yeah.
This was the first time I really had to deal with what I consider pretty high data rates, right? So the
Yeah.
application was like a playback and recorder for RF data
Mm,
um, at variable sample rates. That was the killer, right? I
mm,
want to get your thoughts on. I put together what I thought was a pretty nifty architecture, event-based, and some kind of homegrown actors and things. But I really struggled to debug when the data rate started to pump up because your FIFOs just start to fill up so
mm.
quickly that you've got like sometimes seconds worth of buffers, and then if you've got
Yeah,
a breakpoint anywhere, um, that
yeah.
would just spam out of memory. This was on a beast of a system with like 100 gigs of RAM almost or something on a
Right,
with a nice fancy SSD RAID hard drive system,
right,
but
right.
developing for it was just a nightmare. Like I just really struggled to keep up with the data rates when I was getting up to like 120 megasamples a second and trying to debug my algorithms. Any tips on what I could have done smarter there?
Yeah. So I guess the first question that comes to mind is, did you in a project like that, I would separate out the streaming to disk part. So in other words, have something that's just generating that data, so that way it's not it's. I mean, it could be coming from a VST, but just have an FPGA target that's generating uh, that data rate, and just test out, like, because whenever we have to do record systems, we do separate the record part as a, just have some kind of a source that's coming from an FPGA, because you do want to simulate that large amount of data, and then just because you do need to choose what those FIFOs were, the FIFO sizes. And then I think the other part, I don't know if you were you using the TDMS advanced synchronization.
I tried that actually, but I couldn't get the streaming rates I needed.
Oh,
I abandoned
oh,
that. Is that with the external DVR where you pass
yes,
in and
yes,
yeah, yeah,
yes.
it just didn't. I actually
Oh,
found with with the RAID hard drives, I had better
yeah,
performance doing unbuffered, pure binary transfer. I could
yeah,
write to disk no problem at about like 6 or 7 gigabytes a second.
yeah. So
The
the
issue
writing was
was
is the reading.
I had to display data on the screen. I had to do like waterfalls as well as
Yeah,
recording, and
yeah,
it's just heaps of data pumping around the system, like hundreds of
yeah,
megabytes per second being thrown
yeah.
around on user events, and
What
super easy to
about,
get wrong.
yeah, oh, wow, yeah, yeah, I can imagine. What about, did you have multiple so what about, like, one thing you could do is, you maybe would have FIFOs that are dedicated. So first of all, if you're not using the eDVR, I think that's a big, and I would say I would lean heavily on NI support for that, right? To get some of those configurations right, because um, the only way we've ever been able to achieve like those kinds of rates is with the eDVRs, with the
Okay.
external DVRs. That's one part. Then the other question that I have is, yeah, the other question is, and there's a bunch of things that you have to tune, not just on that, but like on the TDMS file, you have to tune like the number of asynchronous writes and the callers. Like there's a whole bunch of things that need to be configured. So it's good to have a separate project, or like a separate component like that, just gets that like streaming, just because if you can't get that working like isolated, right, like
Yeah.
you want to be able to, or you can always like load it down. So that's one part. But then the other thing I would say is, when you're streaming from you're streaming to and from the hardware for the display, because that is also, that's a common thing as well, right? You're going to need to have some display. Is I would suggest using, like, having separate FIFOs for those, so that way, and configure them purposely to be lossy, because
Right.
what
So
you're going to
actually,
display, like, the user is not. I mean, did you have separate FIFOs?
on the FPGA itself,
Right. So I mean, like, the
um,
data. Well, the data that when you're sending data that's going to disk and data that's going to the display, did you have different FIFOs for those?
essentially because it's using user events, which effectively are their own queues, I guess. At the end of the day,
Right.
on the
With
host
some
level, like
queuing.
a single DMA FIFO to get data to the host, with like an actor dealing with that, and then
Wait.
distributing it multiple
No,
ways.
I think that's where we've done it differently. The way we've done it is we actually had a different DMA FIFO.
Right.
I think what you're saying is you have one entry point, like the FPGA just gets this one set of data, which certainly for the streaming, but to me, like the streaming, let's say it's like 5 gigabytes or 10 gigabytes, it's a certain data rate, like the VST rate, 5 gigabytes per second. But then when you're sending data back in, that's for display, that display is kilohertz really, right? Like it's a lot lower. So we would actually use like a separate DMA FIFO for that. And then first of all, we wouldn't send that much data, like the FPGA would not send that much data up, right? It would have to reduce that. The data reduction has to happen on the FPGA, and then I would separate that. Whereas I guess in your case, you were sending it all to the the LabVIEW, and then you would sort of like just parse it out and just divvy it up to whoever needs it.
Yeah, exactly. And I would do like the selective plotting in LabVIEW. I would say, right, only plot every 100 samples, because obviously it's going to fall over.
You would do your own data reduction, basically.
Exactly. So I tell you why I didn't have separate DMAs is I wasn't confident enough to rebuild the FPGA implementation that NI provided for the VST. There was just too much going on in that, and I had too much else to do. So that compiled, and I had a bit file, and I was like, do I really want to start getting into changing that at the same time as designing this whole multi-sample rate host application?
Yeah.
And I erred on the side of not screwing with that bit.
And that's that may have been, well, it's certainly wise to know that is complex, right? I mean, that is a it is a beast.
It never even occurred to me to have multiple DMA FIFOs. I mean, I'm guessing on the hardware you've got like 3 or 5 or whatever available. You may as well use
however many it has. I mean, The other thing, I guess, could be we're using the second generation VST.
It was the 120 megasample upper limit one. I don't know. They were actually, I had to make it work from 3 different flavors. I don't think it was the brand new ones.
Okay, because the newer ones have the MGT port, the multi-gigabit transceiver port.
Okay, I don't think I had that at all.
So the newer, I mean, if you're saying 120 megahertz, it's probably the first generation ones. But a lot of the newer NI cards, even the 5785 or almost all of them now have an MGT, a multi-gigabit transceiver on the front end. And what that allows you to do is you can actually pipe data into another, you don't want to mess with the VST FPGA, but what you could do is you can actually have that go into a coprocessor like a 7915, and it goes into that one, and that's all like low latency, high throughput, and it goes over there, and then you can do there you can add all those, you can do your data reduction, you can add it's a common architecture, in fact, like the VST with like a coprocessor. And you don't go peer-to-peer. You go MGT. The MGT can go. It's really high speed.
Sure. I think the systems are dealing with NI sold the whole box, and I just had to make it work as the hardware was presented to me. It's like, do this thing.
Unfortunately, the requirement, the hardware was didn't take into account the design or the implications that we've all been down that path. I can feel that. In terms of,
that's a great tip.
You got this hardware. But certainly, I'm glad you asked the question. Thanks for attending as well. Let's see, there's some other questions here. There's one more thing I want to throw in there before we go on to the other question, and that has to do with the shipping examples that come with LabVIEW FPGA. So the eDVR example that I mentioned, that doesn't come with the VST or with the RFSA or RFSG. You actually have to go and look at the FlexRio driver. The FlexRio driver has an eDVR example that does the high-speed streaming. So fortunately, there's examples. Unfortunately, they're not in all of the different kinds of, you're working with one kind of hardware, you're not going to see that in there. And so sometimes you just need to load up all the different drivers that NI has so you can kind of scan for examples. Okay, the first question has to do with have you explained the, implementation of the persistence plot in the RTSA example? The persistence plot, I don't go into too much detail just because it's that code is also available. But I assume that's the guest echo has that question. I don't go into too much detail on the way the plot works. I mean, I do review all the shipping examples that come with the RTSA, because there is some really good, at a high level. But things that are more talking about like the way the plot works, I consider that to be more of a LabVIEW discussion. So I kind of leave that. Don't go into too much detail into that. But that's all these questions are good feedback and things to keep in mind. And the question is LabVIEW FPGA applicable to automotive sensing radars 77 to 79 gigahertz? That's a little bit more of a hardware question. And I do see that the front end of the NIVSTs are using higher rates. I don't know, I haven't worked on anything that's automotive related, but I do know that NI does have like a whole transportation division, and that transportation division is, think, automotive radar. So I think that that is an area that they are looking at. So if hardware, I don't know if hardware exists that goes at that rate, but it certainly seems like it's something that they're following. Okay, and then here we've got a question regarding, I missed the start of the presentations. Are there any examples for high data rates examples? For example, anything handling more than 5 gigabits per second. So for the higher rates, they do have some of their high-speed serial cards. They do have things on that. They do have an example. The FlexRio streaming example does go into, I think, 2 gigabytes per second. So 2 gigabytes should be well above 5 gigabits per second. And then the high-speed serial cards. So high-speed serial, we consider that to be, it's not so much, they're certainly used, but the high-speed serial cards like the 7902, the 6595, 6594, 93, those cards are like, talk about gigabits per second. Those are the high-speed serial cards that support that. So you could look at those. I mentioned the hardware. I'm not saying the hardware so you can go and buy that hardware. I'm mentioning that hardware because what can happen is you have LabVIEW FPGA, you go and you download the driver for that specific hardware. So in this case, the high-speed serial driver, the FlexRio driver, you download that, and then you can go through the examples that come with that. And then you can kind of examine and sort of review those. And then certainly if it's the right hardware, you buy the hardware, obviously. But the idea is that with LabVIEW FPGA, you don't need to own all the hardware to look at the examples and to just get a sense of how they work. Let's see. So we've got a question here from Anders Svensson. Sorry if I mispronounced your name. How do you deal with modularity on the FPGA and host APIs and reuse of code? Say you have code modules A, B, and C. They're independent and do not rely on each other. Each module has a host API to control the module. What if I wanted to reuse A and C in another application? How would you separate the code? Do you call Open FPGA VI for each host API, A and C? Okay, yeah, that's a great question. First of all, it's good to be thinking in terms of modularity. It's good to be thinking that you may use this. It'll all just be used in one place. I would say my recommendation would be the instruction framework, and the instruction framework is something that we've used it, and I would say that is something that's becoming more and more sort of common in our process. And so the idea with the instruction framework is that you could have a subsystem that this is the interface that works with this module, and then this is the interface that works with that module, and then you sort of you bring those together. That's yeah. So that's what I would use there. Do you find that using the instruction framework and modularity outweighs the time compared to using controls and indicators? Well, okay. So first of all, controls and indicators. We should know that adding controls, the more controls and indicators you have on so certainly there's some decisions that need to be weighed when making this decision, right? Like, I mean, there's a bunch of factors that need to be weighed when making that decision. And there is an overhead, right? So to use the instruction framework, to learn it, to be able to use it, to maintain it, there's a bunch of costs to that. So we know that certainly your question recognizes that. And first of all, the one thing that you will have as a blocker is if you put too many controls and indicators on the front panel, you will at some point, that does start to use more CPU usage, because the idea is that every control and indicator is being updated and synchronized with the host because it's a memory mapped register. So it's being updated. And so the idea is that you have too many controls and indicators. At some point, it's gonna, you're gonna be able to use that, but you will, at some point, it's gonna start to use too much CPU usage. So at some point, you just kind of will hit a wall with that. Now, looking at the way, for example, the second generation VST does use the instruction framework. So I don't know what that threshold is where it just becomes untenable to have controls and indicators. But to me, I would, modularity is a tricky thing. And so I would say that it's if you know that you're going to be building, there's an initial cost to that. I think my opinion, I mean, we're sort of, that's the work that I do, right? So we're building these like LabVIEW FPGA systems. So we know that we're going to have, there's common modules, right? There's FFTs and there's filters and there's down converting, up converting, there's other IP. So because we know that we're going to need to have that ability, we're certainly leaning heavily towards the instruction framework. That's if just looking for a yes or no answer, I would say that it is worth it. But again, it just depends on the team. Like you do need to sort of on the right project and all. So now the other question, there's a question from Neil that's using classes on LabVIEW FPGA, so using LabVIEW OOP. I would say that, so first of all, the VST uses classes. That's one place it's being used. If that's an indicator of as to, is that important? The other thing I would say is that if you looked at, I think it's the DRAM example that comes with FlexRio. The DRAM example does use OOP. The DRAM IDLs, the DRAM instrument design libraries use LabVIEW object-oriented programming on the FPGA. And so by having that, you don't need to ever like reconfigure that because you have instances for each of those. I think OOP is good, but I think that just any kind of OOP requires more design. So if you're just going to start coding a LabVIEW FPGA project without OOP, you're going to get into trouble very soon. So usually using OOP, you need to see where the repetition is going to be, where the commonality is going to be. So only when you know that is going to exist, because you may need to iterate on that. You may say, well, that's not going to work that way. So overall, I would say that OOP is something that we should be looking towards for LabVIEW FPGA. But it shouldn't be like the shiny thing that we're just going to use it everywhere, because ultimately that could cause the project to be completely fail. Let's see, and then we've got another question regarding messaging structure using FIFOs. Yeah, so Jason mentioned something about messaging structure using FIFOs. Yeah, the instruction framework is essentially a behind-the-scenes messaging structure. I don't know if that's what you're referring to, but that is what that does. And then there's another question there. Have you covered any example of peer-to-peer streaming? Certainly, peer-to-peer streaming is a critical part of the book, involving data processing on multiple FPGAs. Yes, we certainly do talk about the peer-to-peer, how peer-to-peer works, and latencies that you'll see with that. It's going to be somewhere in the microseconds, the throughput, and what are the things that you have to sort of cover, because peer-to-peer is going to work well, but the chassis and the controller and the different FPGA cards will play a role in that. So we do certainly talk about peer-to-peer. Peer-to-peer is also talked about in the same context as multi-gigabit transceivers, because multi-gigabit transceivers also allow you to communicate with different FPGAs. So that's also another really critical part. But yeah, peer-to-peer is, longer gone, especially with these RF systems, you are not going to build a system that's just going to be on one FPGA. At some point, you're going to have some kind of multi-FPGA communication. Even in Neil's question earlier, right? We had the VST talking to maybe potentially talking to a coprocessor. That's a very common architecture, and that architecture is mentioned in the book. I wanted to thank you all for attending this book launch event. We're excited, and hopefully it's going to be of use. I'm always looking for feedback, and maybe we'll have a second edition. We don't know yet, but certainly your feedback is very helpful. You can certainly post comments into the GitHub, the site that's going to have the the companion website. And again, thanks again for attending. Enjoy the rest of your day.